my name is Jake Whitcomb. I'm on the platform product management team based out of Redwood City, responsible for machine learning tooling and optimization. And I'm joined by Amir Delgoshaie, who's on the product data science team. And I want to frame the next 45 minutes or so around the lens of a data scientist. Now, you learned in the last session that we're actually very focused on a primary accelerator of using C3 AI platform together with multi-role teams, right? To accelerate the AI application journey, it's not teams working in silos, but rather teams working together. But I want to take kind of a moment to appreciate, what I think is a milestone of reaching. I think we're closer to 150 data scientists now. And these are the folks that you're going to see in workshops, in delivering trials and pilots together with you, sitting side by side in a center of excellence, delivering on a use case. And you might have one or two or three of these data scientists embedded. And I think taking the lens of a data scientist is interesting here because I want to address the question of productivity and think about what does it mean to achieve excellence in data science in building an AI application. And this is the first metric that actually kind of sets the sort of stage for how you think about the AI journey with a data science team. Excellence is not about getting an algorithm or a POC to the top-notch accuracy and handing it off to a team. And it's even not about taking it one step further and getting that algorithm to generate predictions into a dashboard and sort of delivering that dashboard and then moving on to the next project. Excellence for AI applications has been about our ability as a data science team and with our supporting teams, the AI application development team, which is all the roles that Kashdab and Joao talked you through in the last session. Application developers, data engineers, data scientists, IT ops, and data engineers. And delivering valuable models to production that generate insights and drive business value. So the measure of excellence is not about how accurate is this model. The measure of excellence is one step further is how successful am I in encoding signals from the data into models that make it to production and deliver value through an application against a business use case. So that's the end goal, and that's the measure of excellence. So how do we, in C3, achieve this together with your teams? So first, and we're going to spend a little bit of time talking about the methodology, because I think this is about people, technology, and process coming together to achieve these results. And then we're going to go deep into the technology and show you some of the new features. At a high level, how does this improve data science team productivity? First, you spend less time in the C3 AI platform on either end of the life cycle. One end of the life cycle is your data engineering, right? Wrangling data pipelines. And the other end is getting models into production, right? Building prediction pipelines, debugging those in production. And we've trivialized either end of this data science life cycle to shift the focus more towards, for the data scientists in the room, the middle part of the life cycle, which is building predictive features as reusable components that you can share within the team, and developing better models, right? And so by trivializing either end of the life cycle on the model ops and on the data ops side, we can actually shift what we found oftentimes 80% of data science teams working on either end, shift that work towards the middle instead. The second is we leverage best-in-class tools and runtimes with no compromise. And what does that mean, no compromise? It means if you have an existing tool in place, you love Vertex AI, I love Vertex AI, you love your SageMaker notebook, you want to run on a particular class of GPU or in Spark, we can make those available, right? And every use case, whether you're doing a large language model to do some transfer learning on top of a pre-trained model for a generative AI problem, or a computer vision problem, or a time series classification problem, require different tools and runtimes. And so we're making these flexible in C3 to data science teams. And I think importantly, it's about choosing a platform that as new technologies come out, you'll be able to adopt them, that you don't, maybe a technology you don't even know about, a year from now, right? So data science teams are not only working together with application development teams and data engineers on a single application, but the components that you're building throughout the lifecycle are fully reusable. And let me talk about how that's different before we get into our specific technology in our current offering. First of all, let's look at common challenges along a typical MLOps pipeline. So what we see in the field today is teams are spending a lot of time building, for start, data pipelines. What is this? I'm writing SQL queries against a data lake. Oh. I'm going to turn this off. And the SQL queries generate a data set that I can use for training data that I plug into a machine learning model using open source frameworks, right? And from this model, then I maybe deploy this as a REST API endpoint to some service so that I can then tie this into an application downstream or a dashboard using a prediction pipeline. And then once that experiment kind of proves out and I get some results, then I do some validation of those results and I hand it off to somebody that kind of refactors that to work on in a production setting with a second pipeline. This is sort of automatically, this is a new auto PowerPoint. Apologize. Yeah, generative PowerPoint. And so now this leads us to a couple good POCs, and I think you can, if your task is to kind of build one project a year and spend time on really customizing a pipeline, this may serve a use case well. The challenge is data scientists spend, for these two pipelines, which is really serving one model, getting one model to production. You may have created 4 custom data pipelines, right? 2 for data generation and then 2 for actually operating these in production. And then in between all of this, you have to orchestrate these data pipelines, the models, deploying to an endpoint, and potentially other components. And all of this pipelining and orchestration, you may plug in some CI software off the shelf, is additional custom logic. Again, you're not much reusable going on here, lots of one-off. So solving this is achievable. You can solve some use cases here, but ultimately, what will you run into next as your big challenges? And these are kind of a handful of them. How do you approve and register models, especially if you're in a regulated industry like financial or government or healthcare, where you have actually regulatory requirements about model risk management? How do you approve and register those models? How do you incrementally update and make these pipelines dynamic as new data and new assets are introduced to the system? How do you incrementally refresh those feature definitions without having to refresh the entire data pipeline, which gets very expensive and slow? How do you validate and deploy new features, runtimes, and models to a live production system? If your performance starts to degrade in production and your training system is over here and your process is 3 to 8 weeks, by the way, double that number if you're in a regulated space, then you're losing millions of dollars of a degraded model in production just trying to get the new models and features in. How do you route new prediction requests that come in to the correct model, whether you're the champion, challenger, canary models, et cetera, and live swap those out in a production system if you have degrading performance? How do you automatically store and monitor historical predictions over time and store interpretability results so I can go back and if a regulator or my colleague asks me how exactly did this prediction, was it made, I can trace it back to the transformation logic, to the model, the champion challenger, the features, the feature snapshots, the transformations that went to that data model, and all the way back to the source system. This ends up being a hard challenge to scale. And so I imagine some of us have gone through this in the past. So let me talk about a new methodology. So C3 provides a reusable set of components throughout the AI development lifecycle. And so instead of building custom data pipelines off the bat, you're working from a unified data model, right? You've pre-integrated the data from either virtualized source systems or data that you've loaded. This could be a single data lake, but this could be, oftentimes we see up to, 20 to 30 source systems plugging in. And these systems could not only be, systems from your organization, but also external systems that you're bringing in to model in a unified way, providing data scientists and application developers and the entire team a unified access layer. So I'm not having to write special unique queries for each source system in building these custom data pipelines and then figuring out why your data transformations are different. And this is about choosing a methodology to work from a unified data model that is modeled after a business use case. This is the first transformative layer. On top of that, we're building reusable features and feature sets, right? These are the data transformations that a data scientist writes to transform raw data in the data model into a predictive signal that I can feed into a machine learning model to either train or process some results. These features are fully reusable, they're composable, I can write them in the interface of my choice, so we'll get into more detail. Then we feed this to a model. How are models composed? Using still the best, open source or pre-trained models in the industry from academia or my own custom code. But the framework here is set up in such a way that I'm building models that can be deployed to production. If 1 out of 100 of my experiments goes really well, I can easily deploy that. I'm building models so that they're fully transparent, so they can be shared with my colleagues. So we have a model registry that it provides a host of capabilities for model validation, model security, model auditability, and so forth. And then I need to deploy these models, so we have a model deployment framework that allows us to easily integrate these models with the production environment, the application. And so if you were listening to Rowan Curran this morning, he spoke about the importance of a model ops capability to integrate models with a production setting. This layer, model deployment, allows you to quickly route all of the model and all of the dependencies to that production application, so I can quickly deploy champion challengers, rollback, et cetera. And if you look at the application on the right, this is the application C3 reliability. It's 7,000 models in the average deployment. And I thought this was a timely example because a year ago this day, 7,000 models seems like a lot in one of these applications. A year ago this day, the predictive maintenance application at Shell announced a major milestone of 11,000 models. And so this is one use case scaled across an organization, scaling and automating the training of now 11,000 live models. And that's not even thinking about all the experiments that were evaluated and discarded in the retired models, but these are 11,000 live models in a production application of predictive maintenance. So how do you achieve this? Let me talk a little bit about the different tools along this life cycle in the next about 5 to 10 minutes, and then I'll hand off and we'll show you this live demo, soup to nuts. So the first tool is the Managed Jupyter Lab Notebook, right? We have a sort of a principle in product development at C3 where we want to provide a native interface to data scientists, right? A native interface to application developers, a native interface where the team expects a certain behavior. For example, best-in-class tool like VS Code or Jupyter Notebooks provide that behavior. What's unique here is that we provide this laptop-like experience, but we're actually in an on-demand auto-scaling cluster. So I can select, I need a GPU, or my ops team can make available, different resourcing sizing, and I can just, as a data scientist, I can select the resource that I need. Oops. From there, we have centralized runtime management. So how do I deal with open source libraries? How do we do that in C3? Well, we have a UI for a runtime management where I can select my open source libraries, solve the dependencies. If you've ever dealt with solving dependencies in libraries across Conda and pip libraries, it can take you like multiple days to get that right. And if you have a certain combination of libraries that work in Jupyter, it doesn't mean they're going to work on at scale on an A100 when you're doing that model training at scale. So we've solved this by providing centralized runtime management, where this tool solves the runtime dependencies across the runtime requirements of Jupyter Lab as well as the available infrastructure. So any runtime that I create in C3, and that can be using my custom registry or any open source library, also can be pre-scanned for security checks, are guaranteed to run at scale in the production cluster. So we're not doing everything in the Jupyter Notebook. We're rather using the Jupyter Notebook as sort of a thin client, as Tom described this morning, where you are using sort of declarative machine learning techniques to push all the workloads down to the cluster on these runtimes. And then finally, enhanced collaboration. We're in different containers, we're running different resources, but we need to be able to share files. So we provide a Dropbox-style collaboration mechanism. Then we plug, the next step in the pipeline is the feature store. We've provided a very unique offering here in the space. Usually a feature store is where data scientists are publishing sort of tables of data used for training or prediction, and then sharing those actual feature snapshots with the organization. The challenge is there's little reuse of the code that generated that feature. So we've flipped that on its head and provided first a framework for storing the feature definitions, the recipes, as metadata that can be tested in the code and shared. Then optionally, you can cache the data. You can store the actual feature data, and this is the kind of classical feature store. If you primarily focus on the former and just on storing the data, you end up with a lot of data scientists publishing different copies of the data, which gets very expensive and hard to reproduce those files. If you flip it, as C3 is provided, we're providing you a way to store the feature definitions, whether you write them in pandas or whether you use our composable expression syntax, which has 150 feature primitives like sum, min, max, interpolate, that you can chain together and build powerful features from day one. And then finally, these features you build once and you can, provide them to the rest of the organization in a production setting. The next tool along the life cycle is the ML pipeline. So C3 ML pipelines provide a composable framework for chaining together multi-step algorithms. And this is critical for data scientists because in the kind of certain ways of doing data science is you can kind of stay in a Jupyter Notebook and write a long script and custom code, and you may solve the problem once. It becomes very hard to debug. It becomes hard to performance optimize each step. And it becomes hard to extend. If I want to take Amir's pipeline and then say, okay, this is great, but I really want to add some post-processing steps on top of it, it benefits me to use a composable pipeline framework. So the industry has really moved to something, moving towards in this direction. These are open in that I can choose any open source library. We have a library of out-of-the-box components. I can also download pre-trained models if I'm, want to pull a large language model off of Hugging Face and download that or do a deep learning model for computer vision on this. This is solving computer vision. This is solving NLP forecasting across the gamut of use cases. These are fully transparent. We're going to demonstrate this. If I come onto a project 2 weeks later after Amir trained a model and I want to say, how did this model get constructed? I can pull that model out of the registry, fully visualize that model, the full, what we call a DAG architecture, directed acyclic graph, and I can even convert that to the authoring code that Amir originally used to create that pipeline. So we have full reproducibility, and then we can run this at scale. If I need to run one of these nodes on a GPU, but the rest on a low-cost CPU optimized machine, I have that flexibility. If I want to push the entire workload to Vertex AI or SageMaker, I can do the same. We have pre-integrated with the cloud. Next is model ops. So I've built my pipeline, I've trained the models. Now how do we port this to production? Now this is a critical step here where it's not about just handing off the model to an application development team to route this into the production setting, right? We have to be able to manage these at scale. We have to be able to roll back. We need a framework to handle this, and we need to not spend time as data scientists debugging, the custom logic that was used to rebuild my model. So, model deployment framework on the left-hand side provides a way to take features and ML pipelines and publish those by way of the model registry to the production setting. So what usually happens is we'll plug in a QA system to through the model registry. We'll import that into the QA system, validate those models. A lot of that validation can be automated, by the way. Like one of the validations you might want to turn on as a company, especially if you have model risk management practices, is an approval process where you can't pull in the model unless it's approved by a particular role. These are all configurable. A lot of our financial institutions have actually configured this to meet their specific auditing requirements around auto documentation, auto approval, and so forth. And then once those models are deployed, we set up the scheduling and routing and the prediction handling, all automatically handled by the platform. On the bottom layer, now these models are running in production, I may later want to add on monitoring and alerting. So automation on top of my running models in production, all to get to models running in a production setting where I can either automate the rules for promoting and demoting models, retiring models, or provide a human in the loop to actually investigate models that are alerted for degradation, for feature drift, for different types of alerts that you might set up as a team. So now let's move over to the demo and give you a brief overview of what this looks like end to end. We're going to look at a use case of a predictive maintenance fleet expansion. My organization and the team that Amir is working on has had a successful predictive maintenance application running for wind turbines over the last couple of years. And now in this scenario, we're asked to train for a new class of wind turbines that are coming online to prevent unplanned downtime. And so what we're going to do is we're going to import some models from the model registry, 2 models, a Keras model and a random forest model, that were used on my prior project. And we're going to use these as templates to expand as baseline models into my new class of assets. My new class of assets are 2 classes. There are 4 Siemens wind turbines and 2 GE wind turbines. And these turbines we're actually going to segment into subsegments of the data population and train 1 global model of the Keras model for either. And then we're going to have another strategy, which is for the random forest model, we're going to train an instance of that for each asset. So we have 2 different models and 2 very different modeling approaches. And then we're going to deploy all of them, a champion challenger for each asset, and battle the 2 and auto-promote the best to champion. And we're going to do that in the next 15 minutes, not 15 months. All right, so welcome Amir Data Scientist to the stage. Amir Delgoshaie.
Thank you. Awesome, thanks Jake for the introduction. So let's build this. As a data scientist, I joined this project, and the first thing I do, I go to the application canvas, right? I have a wind turbine application, and I go to the canvas. Why would I go there? Because I want to get familiar with the data model. I want to know what are the main types. For example, here I see that the central type that is connected to everything is wind turbine, right? If I click on it, I can see the fields on this type. I can see what other types it's connected to. If I click on it again, I get more information on the right. I see details about whether or not this type extends any other type, it has mix-ins, etc. Once I've viewed my data model and I have an initial idea of what's going on, I can move to the Model Ops tab and go to Model Registry. And here, for example, I will search for Keras. And I will see that there are multiple Keras models. Let's assume I know the first one is one of the models that I know is a good fit for this project based on the previous experience that my team had. So I'll click on it and I'll say load this as a model. I will load it as a model so that I will get both the pipeline that was used in the model and also the features that are intended to be used with that pipeline. So once I've loaded it, and assume I've loaded the other one as well, if I go to the application models, I'll see that there are 2 untrained models in my application that are ready to be used and trained. Okay, now that I'm sure I have the 2 models loaded, I'll switch to the Jupyter service of the same application. Here, the first thing I want to do is to inspect these models. So first I will load them. This might take a second. Okay, so here we see, let me zoom in a little bit more. I know it's a little hard to see in the back. Can you guys see anything back there? So? Okay. So I see we have 2 models. Both of them have pipelines and 2 feature sets attached to them. So let's dig deeper. First, I want to inspect the pipelines. What I will do is I will get the pipeline object out of the model object and then visualize its computational graph. I'll do it for both models. Why would I do something like this? Because I want to know what machine learning techniques were used to build these models, right? I want to do a sanity check, see if the techniques are relevant for the problem that I have. So here I see that this first one is based on a random forest classifier. It has some scaling steps in the beginning, and then the output is a probability and some precision score. Okay, so that makes sense. I think I can use this. And then I do the same for the Keras model. I see it's a lot more complex. But at the minimum, I see that it has the same precision score and it's outputting the same predictions. So I know that these 2 are apples to apples comparable, right? So now I inspected more or less the computational graph. As Jake mentioned, I can also get the authoring code for these pipelines. So I can look into the details of how these pipelines were generated. So for example, I see that there's a standard scalar step. I could copy paste this code and maybe substitute the scalar with another scalar that I see fit. Or I can add additional steps in between. So let's say at this point I'm happy with the pipelines and I want to move over to the feature sets. Okay, so for the first model, I can see the details of one of the feature sets here. I just grabbed the object from the data model of the application. So here I see, for example, it's a feature set on an hourly interval. It has 3 features, and it's engineered features based on measurement data in my application. So, okay, so far this makes sense. I can also dig deeper and look at the authoring code of the features. For example, here I see that this active power feature is on the wind turbine source type, so the source type makes sense. I can also see the transformations that were used in the recipe of this feature. Again, if I see fit, I can make any changes that I want or create a similar feature, but for the sake of this demo, let's assume that things are good and we want to move on. Now, so far we saw the feature recipe. Now, because these features are materialized, I can evaluate the feature values for any of the wind turbines in my application. In this example, I'm evaluating this for turbine 3. And here you can see the results. The return object is a C3 data object, which exposes a lot of pandas-like APIs. As an example, I'm using describe here, right, to get this summary statistic. As Jake mentioned, and you can imagine, there's a lot of calculations going on in the background for getting all this statistical summary. All of this is happening on our distributed cluster, right? And only the final result is shown to the user. Why is this important? Because in a real application where we have big data, right, we don't want to be constrained by the computational resources of our Jupyter service, right, which is usually much smaller than what's available to the application in the cluster as a whole. Okay, so moving on, I will also visualize the features to kind of look at the time series like I would do in any other project. And note that for visualizing, I'm just using Matplotlib, so the tools that I'm used to and I like. Okay, so far we have inspected the pipeline and the feature sets and everything makes sense. Now we want to actually train the models that Jake mentioned in the setup. Just a quick reminder, what we want to do is we want to train one Keras model for all wind turbines belonging to the same manufacturer, right? And we also want to train one random forest model per asset, right? So to do this, we need to follow 3 simple steps. One, we define a training strategy. Training strategy is basically defining the instructions for getting the data for training. As an example, when I said group by equals manufacturer, I'm telling the training strategy that to train this model, go pool all the data for the same manufacturer together and then use that for training the model. So far we haven't specified which model. That's step number 2. We define a train template, which is really a template based on the models that we loaded from registry. And then last step is putting these 2 together in a training group. Training group is really just a combination of a template and a strategy. Now that we have our kind of setup done, we can kick off a training job. What this job will do is it will kick off the training for all of the models that I specified. And we have to wait a little bit, obviously, because there's a lot of models, but once it's done, you can monitor the summary of the job. So now, why is this important? Because as you can imagine, as you saw in the demo, in a typical application, you can have hundreds of assets and maybe thousands of models, right? Training and deploying these models individually can be a very tedious task and sometimes impossible. But this job, what it does, it provides a simple interface that does all of this orchestration for you, and it also maps the computation to the C3 cluster, right? So the computational part is also taken care of for you. Now, another thing I want to note here is that none of this code for setting up the training job would change if you had 10,000 assets versus like 5, right? So you don't need to worry about changing anything here if you want to scale to a much, much larger application. Okay, so now we have trained all of our models. We simply deploy everything. Deployment happens in one line. We just say model.deploy, and let me just close this. As we expect, after deployment, we have 2 models per asset. So for example, for wind turbine 1, we have 2 models, both of them are candidate, because initially when you deploy something, the status is a candidate. Now, let's promote the best model to be the champion. How do we do that? We pick up a holdout test set, and we compare the 2 models on the performance on that holdout test set, and automatically promote the best one by setting the status to champion. After this step, as you would expect, we would have 2 models per asset. One of them will be the champion, and the other one will be the candidate model. And finally, now that we have deployed model, we can grab any asset in our application, for example, turbine 1, and we can make predictions by calling the process API. And because we have model deployed to this asset, we can make predictions using any and all of these models. And even better, all of these predictions will automatically get persisted to our application. So now that we've trained our model, if I go back to the application canvas and go to our deployments and zoom out a little bit, I will clear all the filters. So we see the same asset turbine 1, and we see the fact that it has 2 models deployed, and we see the status that we would expect for these models. So given the right permissions, a user can also go in and promote these models using the UI interface versus the notebook, right? So to recap, if I go back to the setup, we started from 2 untrained models in model registry, and using very simple steps, went through all the steps of model development and deployment for a relatively complex deployment, right? We had a champion-challenger deployment. Why was this possible? Because we used the data model and all the reusable portions of the data model. We also used reusable artifacts that were built by other teams, such as pipelines and features, right? So now as a data scientist, I'm pretty confident that I'm starting with an application that has all the ML pieces working end-to-end. And I have 2 models deployed for each of the assets that my team is interested in. So now what I can do is to focus my time on the asset that don't have a good model or don't show good performance, and go dig deeper into them, do some root cause analysis, and maybe spend my time on additional feature engineering or model tuning and development there. This concludes the demo. If you have any questions, we'll open up the floor to that.
Nice. Questions? I know we're at 5:30, and some folks might have to step out, but we can stick around for any follow-up. That clear?
Yeah, very convincing.
Nice. Thank you.
Thank you.
Yeah, Shara in the back. Yeah, please. All right. Oh, go ahead.
I was thinking if these capabilities are available to our customers. Are these capabilities available to our customers yet?
Yes, so the capabilities that we're demonstrating here are with version 8 of the platform. 8.2 is what we're demoing today. And this is 8.2 is actually being cut right now. So this is a live. This is Scott. Is Scott in the room? Yeah. This is 8.2 is being released. If it's not today, it's any day. So yes.
I have another question.
Please.
How long do you think it will take data scientists to learn the new techniques compared to version 7?
Do you want to take that?
Sure. I mean, there will be some learning curve, but I think it's significantly less steep compared to V7. I mean, as you saw, most of the APIs are very simple and intuitive. I had I think less than 15 cells for completing all of this workflow. So I'm pretty confident that they will be able to learn this quickly.
If you're learning this version compared to a previous, I think there are a couple areas where you'll find things are much more natural to maybe a tool that you used in the past if you weren't familiar with C3. One on data wrangling and feature engineering. Now that we're providing the datasets interface, which is effectively a Pandas API that's backed by a distributed cluster, you're able to use straight Pandas. If you're familiar, most data scientists that write Python are familiar with Pandas for feature engineering, and store that code as reusable metadata. So we've solved the scaling problem of Pandas, but we've provided a production-ready code as well. So that's one area where I think onboarding is going to be a very nice experience for feature engineering. And on the machine learning pipeline side, we've provided a Keras interface, which is called functional authoring. So Keras provides a way to link together DAGs that's, in the declarative ML space has kind of been thought of as the nicest interface, and we've applied that same methodology to any type of pipeline. So if you're doing a computer vision model or NLP model or stitching together something else with, random forest classifiers, you'll use the same Keras functional style authoring. And then if you want to build a custom pipe, you no longer have to go and pull up a separate IDE to write that custom Python, but you can write that custom Python class directly in Jupyter and wrap that code in a pipe without leaving Jupyter. That's why we've kind of really emphasized use the tool that you love, and Amir loved the Jupyter Lab notebook, so we saw a lot of that, but augment it with other tools like user interfaces, our Model Ops UI, Global Canvas UI. These are new that will, I think, help data scientists learn this version of the platform.
Another question?
So
Yes, Juanes.
you had the 2 models. One was a scalar pipeline, and one was Keras. But would it also work similarly if you want to mix models that you made in other environments, like R or SAS?
Yes, any runtime. So any of these models can have their own runtime. So you can actually have a runtime for a model. I don't know if this is A2, but you can also have a hardware profile per model. So everything customizable per model.
So within that notebook that you showed us, you just refer to the model and the runtime is defined within the model.
That's right. So if you have the model in the C3 environment, wrapped in a pipeline, we actually have control over the model artifact. That will run in a C3 runtime and will spin up the resources required. Now, if you have a model that let's say you have a model living in Vertex AI and you have a model in their model registry and you just want to connect to that and you want to leave that in place, you can also create that as a virtualized model. And using an ML pipeline from C3, you can basically, when you get to that step, the system will know to make an authorized request out to that endpoint, get the results back. And that way you can actually bring to production these endpoints that are living in a third-party production system. We're using the same methodology for going to production. So you're not having to then create a custom way to do your model ops, but rather you can just treat that model as a virtualized model. So there's a few different options if you want to leave those models in place, but you can also import them into C3 runtime.
And that includes any other commercialized things like SaaS and all of the other platforms outside?
Yeah, yes, all. Yeah, all is, great follow-up question, Elizabeth. We have lots of integrations and, so our big partners, Vertex, the GCP team, SageMaker, Azure ML, all of the Conda and open source libraries from Conda, pip, CRAN, we can talk about more connectors yeah. Thank you. Thank you for the extra time as well.
Thank you.